Welcome back, everyone. I did something terrible. It's terrible yesterday. I went outside, and so I didn't do day 6 yesterday when it was December 6th. So today I'm gonna start day 6, and then I'm gonna like put on a hat, and then we're gonna do December 7th. So don't tell any of my YouTube followers that both of these recordings happened the same day. I want them to think that I slept in this shirt and then recorded during the morning of Friday, like when I should be working or something. Anyway, let's dive into it. We're gonna figure out what day 6's problem is, and we are going to solve it together. Not with this. I didn't do my normal template prep here. Boom. But we're gonna get started with a brand new Ellie here, and we're gonna go hello. And this is going to show us the code, the output on the right, we got the code on the left, and we're going to work through the problem one step at a time. And that is how we do it here, folks. So let's take a look at the problem for the first time and figure out if it's going to be a bumpy ride or a very smooth ride. All right, day 6, Guard Gallivant. I think that's how you say it. The historians use their fancy device again, this time to whisk you away to the North Pole prototype suit manufacturing lab in the year 1518. Turns out that having direct access to history is very convenient for a group of historians. You still have to be careful of time paradoxes, and so it'll be important to avoid anyone from 1518 while the historians search for the chief. Unfortunately, a single guard is patrolling this part of the lab. Maybe you can work out where the guard will go ahead of time so that the historians can search safely. You start by making a map, which is our puzzle input. I'm going to copy that. So it looks like a bunch of dots and hashes. The map shows the current position of the guard. Oh, here we go, with a, whatever that is. A caret? Is that right? Am I out of my mind? I think it's a caret. With a caret to indicate the guard is currently facing up. This is hilarious. All right, any obstructions, crates, desks, alchemical reactors are shown as hash. Lab guards in 1518 follow a very strict patrol protocol, which involves repeatedly following these steps. If there's something directly in front of you, turn right 90 degrees. Otherwise, take a step forward. Following the above protocol, the guard moves up several times until she reaches an obstacle, in this case, a pile of failed suit prototypes. Because there's an obstacle, you turn right before continuing straight in the new direction. Reaching another obstacle, a spool of several very long polymers, she turns right again and continues downward. So she's kind of like going like this. And so she keeps going until until they walk off the mapped area for walking past the tank of universal solvent. By predicting the guard's route, you can determine which specific positions in the lab will be in the patrol path, including the guard's starting position. The positions visited by the guard before leaving the area are marked with an X. In this example, the guard will visit 41 distinct positions on your map. Predict the path of the guard. How many distinct positions will they visit before leaving the mapped area? Okay, so this is good. So we've got this stuff here. I'm going to paste it. This is our map and where our guard is. Oops, I think I grabbed the wrong one. That could have been annoying. That's our puzzle input. And so we've got the guard starting here. I want to see if it's inclusive. Including the guard's starting position. Great. Okay, cool. Okay, so what we need to do is we need to take all these characters. You'll see there's a bunch of characters on the right. We need to turn this into a map. So let's make a map. So a map is kind of a dictionary of coordinates to like what's at that coordinate. So I'm going to say, we're going to call it a tile. So a tile can either be, I'll call the location. That won't be confusing with coordinate, will it? All right, let's not call it that. All right, the tile can either be empty or it can be an obstacle. So you can also model this with a Boolean, like true or false. Is it there? Is it not? But the idea is we're going to want to map like 0, 0, 1, 0. All of these are going to be inserted as empty. We could also say that we're going to have a set of coordinates called like the obstacles. And we can just say if it's not in the set, we don't worry about it, and then we keep track of the bounds. So this can be obstacles. I guess we can still call this map. And then we can have the bounds. So we can have the max x is int, and the max y can also be an int. This will probably be a little bit more space efficient. So I'm just going to do it just to be safe in case the puzzle input gets really big and we're inserting a lot of like blank cells for nothing. So I'm going to call this the number of columns instead. And I'm going to say number of rows. So columns are going to go left to right, and then rows are going to go top to bottom. So what we need to do is we need to basically take this, we need to import set, exposing set. So I'm going to take that input string, I'm going to turn it into a list of strings. I'm going to define the coordinate type to just be 2 ints. So now we've kind of got an array here where each of these elements are going to represent like each line in our thing. So what we're going to do is we are going to list.index map these so that each row, each one of these lines represents like the y value. And then what we want to do is we want to return basically another list. List.index map. I think we want to do a list.index map one more time to get the x's. And then what this is going to do is give us the x and the y, and it's going to give us like the tile. So this is going to be each line. This is going to be each character at that line. String.lines. We're going to do string.toList for that line. And then this will give us a list of characters here. So I think by the end of this, oops, I think I lost a parenthesis here. Let's format that into place. We're going to end up with a pairing of each coordinate with what ends up going there. So here we kind of have like this grid of all this stuff. But what we want to do is we want to kind of take all these and then build up a map. So what I want to do is I want to say, I've got the list.index map. Now what I want to do is just filter the ones. So we'll do a list.concat to kind of flatten these nested lists. Now we got one big flat list of all these points. And so what I want to do is I just want to keep the values that have a hash in them. So I'm going to say list.filter, and we're going to say this is the point. This is the char here. We're going to say keep it if the char is equal to this hash here. And so now we've only got these, and so what we can do is we can probably just do this all in one line with the filter map. What we're going to do is we're going to say if the char is this, then we're going to return the point. And we're going to keep the point. Otherwise, we're going to discard the information and do a nothing. So I'm going to format this. And so the idea here is that this function say 2 points. This took a list of strings and it returned a list of coordinates. Oops. Characters. Oh, sorry, this takes an int and a string and returns a list. That, and then what this one did was it took to hashed points. It said, I'm going to take in one of these coordinate char things, and I'm going to maybe return a coordinate if that coordinate is a char to hashed points. So that's the idea here. This was the input. Sometimes I like to take the lambdas and just kind of give them names. These names aren't great, so I'm going to kind of revisit this. 2-point char pairs. And then this is going to be 2 hash coordinate. I'll say 2 obstacle coordinate. Hash is a little silly. So then this is what we use here. This is what we use here. This gives you a little bit better sense of like what the inputs and what the outputs are to the function. And then if we wanted, we could also kind of break that apart. I'm going to leave this alone. This is just an int to char, and it returns one of these guys here. So now that is a list of where all the obstacles are in our grid. So what we can do is we can say set.fromList, and that's going to give us a set. And what sets allow us to do is say, set.member, set.insert. It makes it easy for us to say like, I've got a point. Is this point in my set? Yes or no? Lists are kind of annoying because you have to like loop through them and kind of scan. So what I'm going to do instead of this is I'm going to say, let's take all of this, let's leave it as is, but I'm going to call that puzzle input. So this is going to do that. I think what I want to do is have the puzzle input just be that first thing that we had. So I'm going to call this puzzle input. And the puzzle input is going to be a list of these coordinate char things. So there you go. So list coordinate char. So what this did is this allowed us to find our obstacles, which was a set of coordinates. So that was what we did so far. We also need to find our bounds. So what we can do is we can either take this string and get like the first line's length. I don't know exactly how we want to do this, but so far this is what we had, right? We have this set from list, but we're going to need to get other information. So what we want to do is we want to get like the length of the first line, and we want to get the total number of lines. So I'm going to kind of move this in here and say, char pairs is going to be the puzzle input, and then we're going to apply this to that, and then this is going to go here, and then this is this, and this is just going to be a list of strings, because we're going to want to use that list of strings to be able to figure out the number of rows. So the number of rows is going to be the length of the list, how many lines we have. So this will give us an integer. And then we're going to say the number of columns is also going to be an integer. The puzzle input could be empty. So what we need to do is we need to say get the kind of the first line. So these are like the puzzle input lines. I'm going to call it that. And what I want to do is say get the first line and then try to get the length of that string. And if you didn't get a line, if there were no lines, you could just say 0. But this will, this maybe with default will hopefully give us the 0 we're looking for. Oops, I forgot to do the equals line here. Puzzle input, oops, puzzle input lines. Great. Okay, so let's return all this stuff here. So let's make that map. So the map took the obstacles, it took the number of columns, it took the number of rows. And so I'm using these variables and just kind of putting them in that map constructor. So now we know that we have 10 columns, we got 10 rows, and we've got 10 whatever. If this was shorter, we'd hit 9 columns, right? There we go. 9 columns. So it's the length of this first list is what's telling us how wide our puzzle input is. Okay, great. So we've got the columns, we've got the rows, we've got this. So we've built our map. So now we want to run logic. We also need to know where the player is, right? So what we're going to do is we are going to say the player is something that has a position, and it has a direction. So in Elm, we can make a custom type for direction that represents, like, you know, northeast, southwest. That's one way to do it. So we can say north, east, west, south. Another common way to represent direction is to kind of have two ints. So north would be 0, and then if you want to go up, it would be -1. Yeah, because it would decrease the current row. South would be 1, and then you'd have something similar. So west would go that way. East, oops, would go the other way. So east would go right along the X, because our 0, 0 starts in the top left, so south would increase it, and north would decrease it. That's the idea there. So all of these would be directions too. So do copy. What's nice about representing directions as points is that we can add them with coordinates, and that'll give us the new position. Okay, so we've got the number of columns, we got whatever, and now we need the player. So we need to figure out, based on our map, where is the player located. So that's why the point char pairs came in handy. So the player, what we're going to do with the players, we're going to start by saying, let's comment this out. Let's start with where we left off. So we left off with this point char pairs. What we want to do is we want to find which one is this. So what I'm going to do is I'm going to say filter this so that the character, I'm going to do a filter map actually. So filter map is going to say if the char is this, then we're going to say we're going to create a new player at that point, and we're going to say the direction is facing north. And for everything else, we'll say that we didn't find a player there. So when we scan through all these points, it goes through each of these, and it can't find any carets until it finds this one, and then it's like, got it. This is north. So I want to see if we can support less than, greater than, and v, because I think I just want to see if our puzzle input okay, looks like we just have the one. We don't have any like less thans to worry about. So we don't need to scan to see like, oh, like initialize him in the north direction, the south direction, that kind of thing. But we will want to have these for when we implement the turn function. So putting all that together, now that we have our player, we can annotate this here with player. Sorry, this isn't a player yet. This is a list of players. So what we want to do is we want to say list.head. That'll give us a maybe player, and then we're just going to give it a default player. And the default player is just going to say I'm in the top left and I am facing north. So hopefully we never get to this. That's like a bad puzzle input situation. But the beauty of it is we've got this map, we've got our number of columns, we've got our number of rows, we have our obstacles, and now we've got a player. So the player's direction is this, and the position is 4, 6. So as you can see here, if you go 0, 1, 2, 3, 4, and then you go 0, 1, 2, 3, 4, 5, 6, it's successfully identified where that player is supposed to be based on the coordinate. So I think we're in good shape so far. But now that we have our map, let me put this here. I'm gonna give this an annotation. What we want to do is we want to kind of keep looping. We want to simulate. So I'm going to make a simulate function that takes in a map. And what it's going to do is it's going to return the new map, and it's going to keep doing that as long as the player is not off the grid. So we're going to give it a map. It's going to return a new map. And so this is going to be a recursive function that just keeps looping. So here's my map. If I just returned it, it would just keep everything as is. What did I screw up? Oops. The indentation's wrong here. That's weird. Okay, great. So this is not simulating anything. It's just taking the map and returning it as is. There's one thing we need to keep track of, which is where has the player visited. So what I want to do is I want to add that as a set of coordinates. We need to be keeping track of these as the simulation goes on, because the length of this set of coordinates where the player is visited, that's going to determine what the answer is. We're going to use that, and that's going to be the answer to the puzzle. So I'm just going to add at the very end here, set.singleton, starting with the player position. So when the game starts, all we're going to have is where the player started. He or she started at forward 6, whatever the guard started at. So I think guard is probably a better name for this, but that's okay. I'm so used to making games that I name everything everything player when it comes to moving. But if we wanted, we could call this guard, and then it would just be up to us to kind of rename these. I think in the spirit of the problem, we should call it guard. And Elm's always going to help us go through any refactors like this. So I ain't even worried about it. And then player position. But I'm really leaning in the compiler here to catch all the spots that I didn't change the variable. Great. All right, I'm just going to save for a little checkpoint. This is good progress. We're almost there. Most of the work so far was just kind of taking this text format and turning it into a representation. And now we can start writing some logic. So I can say if the guard is off the map, then we're done. We're just going to return the map. Is out of bounds. Map.guard. I'm just going to give it the whole map. Let's make a little expression here. Is out of bounds. Otherwise, we're just going to return the map. But we need to determine true or false. Is the player currently out of bounds? Given the number of columns, the number of rows, and the position of the guard, are they out of bounds? So we can say if guard dot position. Let's take the x and the y. X and y of guard position. We say x is less than 0, or x is greater than map.number of calls. It's greater than equal to. Yeah, because it's index based. So he's out of bounds if any of these are true. Be careful with the copy paste, because I will forget to change something and then we will get the problem wrong. So this will tell us if we're out of bounds. And so if we're out of bounds, we're going to return the map. And then otherwise, we are going to keep simulating. So this is our kind of our base case to make sure that we don't, hopefully we don't loop forever. What we want to do is we want to say, if they're not out of bounds, we need to look at the next, kind of like the next location. This is going to be the coordinate that the guard would move to. So the next location is going to be take the guard's position. And what we want to do is we want to add 2 coordinates together. We want to add the direction to the position. So I'm going to make a add. I'm going to make a move coordinate in a direction function. Direction coordinate. And I'm going to move his out of bounds to its own helper here. Sorry, I'm just going to do that too. That was bad. And this is going to take in a coordinate and tell us if it's out of bounds. Give me the map. That way we don't need this. Move direction coordinate equals. So what this is going to do is this is going to take the directions x, the directions y, and it's going to take the coordinates x and y, and it's going to return x plus dx and y plus dy. This is why we represented our direction as kind of like a delta, is to make this part easy. So what I'm going to do is I'm just going to say move. Move. Take the guard's direction, the guard's position. That's going to give us a new coordinate. What we want to do is we want to check that next location. So is out of bounds takes a map and a guard position. Let me just make sure that this is all still working here. Guard. Ooh, this is going to be map guard. I'm just going to make a little. I'm going to pull this out because we're going to use it a lot. Okay. So all this did is it returned the map as is, but I just wanted to compile it to make sure that all my types are working out. So the next location, we need to say, is the next location an obstacle? So else if next location is a member of the map obstacles. If it is, what we need to do is we need to turn the player. So we're going to turn the player and then we're going to simulate. So we're going to take the map, we're going to turn the player, and then we're going to keep simulating. So turn player is going to take the guard. I keep saying player everywhere, it's going to drive me nuts. Turn takes the guard. It's going to take in the map and return the new map. I think actually we don't need to take the guard here. So it's going to turn the guard. And so all we're going to do is we're going to say case map.guard .direction. I think this will be easier. If direction is north, then we're going to take the map, set guard direction. So if they're north, we want them to be facing east. And then we're going to kind of repeat this. If they're east, we want them to go south. If they're facing south, we want them to go west. Or west, which is what I apparently typed. And then if it's west, we want them to go north. And if we get a direction that's total nonsense, because integers can represent anything, there's just going to be an else branch here where we just don't mess with the map. We just don't turn the guard. So if the guard's not facing any of these predefined directions by some magic, we're not going to do anything to the map. And then I think set guard direction we need to make. Cool. So set guard direction is going to take in a direction, it's going to take in a map, and it's going to return the new map. So this is the direction, this is the map. And so all it's going to do is going to say map guard equals, then we're going to modify the guard. We're going to say the guard's direction equals the new direction. But we need to basically get access to that guard variable. Keep doing that. Oops, can't format because there's an error in my code. Okay, we're getting warmer. So this is, if we're out of bounds, we're done. If we are about to hit an obstacle, then we're going to turn the guard. But if we're not about to hit an obstacle, we're going to move the guard forward. And so moving forward is also going to insert into our visited tiles. And then we're going to move forward and we're going to keep simulating. Cool. And we also want to make sure that we only insert if the thing is in bounds. And that's why I wanted to extract that stuff out. So we're going to do something like this. We're going to move the guard, and we are going to say, what the next location? You just pass in that coordinate, right? Destination. And we're going to say if that destination is out of bounds, where we're headed is out of bounds, all we're going to do is we are going to update the guard here. So I'm going to actually do a cool thing you can do with Elm, which is you can destructure right in your arguments. This is kind of like doing doing like destructuring in JavaScript. So if it's out of bounds, we're just going to move the guard. So we're going to say, very similar to this, we're going to say this, but instead of updating the direction, we are going to set the position that direction. So if we're out of bounds, that's all we're going to do. Otherwise, we are going to update the guard and we are going to insert into the set.insert destination. And I think this is enough to get the rest of the game working. I think this will simulate the whole game here. So I run that, and you can see is all these visited things got updated, and the guard ends up at 710, which I think is where he ends up here. Right, so he's here, and then he goes off the map. So what you'll see is 0, 1, 2, 3, 4, 5, 6, 7, and then instead of being in row 9, index 9, he ends up at row 10. And it says 41 is the length of that set. Let me go up here, and now that we have the map fully simulated, we can do is we can say .visited to just get the visited field. And then we've got that set, and we can say set size, and we get 41, so that's the answer. So I'm going to go over here, admin of code day 6, part 1. I think this was the convention I was using. I'm going to save this, I'm going to copy that code, and I'm going to replace that. These are the day 5 puzzles. So let's try it on our puzzle input. Let's see how it goes. So this still compiles. Let's see what we get. 4883 visits 4,883 tiles. And that's right. So we're doing good. That's part 1. I'm going to take a sip of iced tea, and we're going to click part 2 and see if we can pull it off. All right, part 2. While the historians begin working around the guard's patrol route, you borrow their fancy device and step outside the lab. For them, the safety of a supply closet, you time travel through the last few months and record the nightly status of the lab's guard post on the walls of the closet. Returning after what seems like only a few seconds to the historians, they explain that the guard's patrol area is simply too large for them to safely search the lab without getting caught. Fortunately, they are pretty sure that adding a single new obstruction won't cause a time paradox. They'd like to place the new obstruction in such a way that the guard will get stuck in a loop, making the rest of the lab safe to search. To have the lowest chance of creating a time paradox, the historians would like to know all the possible positions for such an obstruction. The new obstruction can't be placed at the guard's starting position. The guard is there right now, and it would notice. In the above example, there are only 6 different positions where a new obstruction would cause the guard to get stuck in an infinite loop. The diagrams of these 6 situations use 0 to mark the new obstruction, pipe to show a position where the guard moves up and down. Nice. And minus to show where they go left and right. Plus to show, wow, interesting. So this is one way to trap the guard is by putting this O down. That's the new obstruction. Option 2, put a stack of failed suit prototypes in the bottom right. So he goes up, do, and then he kind of gets stuck in this loop. It's the formation. That's the symbol. All right. Option 3, put a crate of chimney squeeze prototype fabric next to the standing desk. So he goes do. Okay, so it kind of like goes in this pattern. It's interesting. Then option 4, put an alchemical retro encapulator near the bottom left corner. Sweet. All right, I feel good about this. I think this is going to be pretty easy to do. Maybe not super easy. How many different positions could you choose for the obstruction is the answer that we want. All right, so let's go back. So it looks like if we do the thing right, we get the number 6. Let's kind of rewind where we left off here. We ended up with a simulation that kept moving the guard, but there was no like stop. There was no way to say like if the guard had already been there. So what we want to do is we want to say is it an infinite loop or not? So what I want to do is I want to update the simulate function. Let's kind of go back here. And this is like the ending map. So what I want to do is say if they're out of bounds, not infinite loop. So there's like, we can return a value here saying like, in this case, they did not get out. So maybe like the result, the loop result. Call it the loop outcome. You know, this is all about business outcomes here. So loop outcome is stuck in loop, got away. So if they're out of bounds, they got away. They escaped the bounds. But what we can do here is we can just say, oops, if the next location is already a member of the visited positions, I think if it's not enough to say that it's the same location, we want to say has guard been here before and is facing the same direction. So what I want to know is I don't want a set of coordinates. I want a set of coordinates and their directions. So I'm going to update visited to kind of represent something else. And once I do that, I got to remember to do that. If I can do that, then I know that because he's facing the same direction and he's in the same location, he will follow the same path that he's done. So this is going to like detect my loop. So what I need to do is I need to update visited to store slightly different information. Instead of storing the guard's, it used to store the guard's position. What I want to do is also store the guard's direction. So we're gonna do both. And so it's up to me to make sure that I don't screw that up. I would just store the guard, but unfortunately Elm's set type doesn't allow us to do sets for records because the field order I think isn't deterministic or something. I don't remember what the deal is. But what I want to do is I want to say instead of a set of coordinates, I want to do a set of coordinates and directions. Coordinate, direction. So when I compile this, I should get an error because when I insert into my set, I'm only inserting the destination. I'm not inserting the guard's position. So that should be easy to fix. All I need to do is put in the coordinate and I need to put in the guard's direction. Guard dot direction. And this is a perfect example of where using type aliases really helps because Here, I could have easily switched up coordinate and direction if I just used int all over the place. So by using a type alias, this actually prevented me from getting a headache when I inevitably switch up these two identical types. So notice that coordinate and direction, they're technically the same thing. They're just a pair of numbers. But this really helps with the error messages. So if you're not going to go full type safety and make coordinates some special thing, like we did with this, because we want to be able to insert these into sets, type aliases go pretty far. Let's see if this works. So map coordinate visited, else if set member next location. So what I want to know is next location. Oops, I'm sorry. Up here we want to get next location and the guard's direction. So if we've been here before and we've been facing the same direction, then we're stuck in a loop. Okay, so see how it says got away? So this is the data that we cared about before. Now all we care about is kind of the second thing. Did they get away? Did they escape the map, or were they stuck? So a way we can make this guard get stuck is we can just put a hash here. And so in theory, he would go there, he'd go here, he'd go here. Oh, that's actually not good, sorry. Let's do one of the places it said do. I think this is one of the places. So if we add a hash here, he's stuck in a loop. So we were able to detect that basically the guard went the same way. And the way that's working is that it's inserting all these new places. And then here, this was the important part. As it's going left, we don't know if it's stuck in a loop yet. We just know that it backtracked over itself. That's why we updated set.visited to also care about the direction, because this is different than this. That doesn't prove that we're in a loop. So when the guard goes all the way past this, here, 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 it's actually this tile. This tile, when they're at, I think it's 5 and, what is it, 9, 8, 7, 6. 5, 6 should be where the guard ends up at the end. So I bet if we asked tuple.first, we would see that the guard's position, oh, it's actually one after that because he steps forward. But the idea is the same, which is that we've seen the guard at this exact place before, and so we want to return basically how many places we can add obstacles. So I'm going to undo this. Oops. I'm going to get rid of that obstacle. And so the guard got away. So what we want to do is we want to basically take this huge grid of numbers. So what we end up with puzzle input lines is we've got the point chars, we got these. What I want to do is I want to make a dictionary out of this. And I want to have like a bunch of updated maps where we can just insert, actually with our obstacles, I just want to be able to loop through and insert an obstacle in each position and then check for that insertion, like did the guard get away, did they not? So the idea here is we would say list.range, going from 0 to the number of columns, -1. This will give us all of the x coordinates. If we do a list.map, this is going to get our x coordinates. What we're going to be able to do is create all these variations of our map, where our map just has different obstacles. So I'm going to actually make map a function that takes in a set of coordinates. And I'm going to rename this to initial. And I'm going to rename this to toMap. So toMap takes our obstacles that we pass in, and we'll come back to this here. But the idea is we've got our x position. We're going to do the exact same thing, range, We're gonna go from 0 to number of columns to get how many potential Y positions we can do. We don't have to make this a list.range. I don't think it's going to give us trouble, but we're basically just kind of generating all these things here. And so we're going to list.map that. And this is going to give us a list of all possible like obstacle sets, which is a little bit crazy. But what I want to do is for each one of these, I've got an X, I've got a Y, sorry, list.map takes an X, takes a Y. What I want to do is take the initial obstacles and do a set.insert at that X and Y. And this will give us a list of new obstacles, list.concat. I think this crazy thing that we just did, obstacles list, is going to give us a list of this set of coordinates. I think this will work. Oops, and I should probably use it. So just to show you, this is huge. This is basically, it's looping through all of these possible things. I think a list range is a little bit of a crazy way to do this. I'm going to be fancy and I'm going to combine my map and concat into a concat map here. But the idea is the same. What we're doing is we're creating all possible variations of the map where we insert something at all these spots. Yeah, that's pretty much it. So what we're going to do is we're going to take all of these and then we're going to say list.map to map. And what it's going to do is it's going to create a map for all of these things. And then we're going to say list.filter. Now that we've got the map, we're going to say simulate that map, and then tell me only keep it if when you're done simulating the map and you get the second value in the tuple, like the got away, if that equals stuck in loop, then we basically want to keep that map around, and then we're just going to get the length of that map, or how many maps did that. And so we get 6. So that was a lot. That was pretty crazy. But basically what we were doing was we were creating all these huge variations of every obstacle where we inserted like all these things over and over again. This isn't very space efficient. We're creating like huge, like a huge set of things, like this every single cell that you see here is going to represent a set. So hopefully this doesn't crash our computer. I don't think it will, but if we do, we'll switch to something a little bit more space efficient. But what I'm going to do is I'm going to copy this and I'm going to save this for the video description, so you can see the solution. You can run it yourself. And what I'm going to do is I'm going to see if this works with the big puzzle input. This is making the crazy monolists, so sorry about that. My computer is now cooking. This is really memory inefficient. So the normal way to do this is that we don't create a list range, and then do this list map stuff. The normal way to do this is we just take our initial thing and we just loop. And we say, all right, take the set and just insert one thing here, try it. Take the set, just insert one thing here and try it with each simulation. Instead of making a huge list of maps, which is just crazy. So I'm glad this crashed because this should not have, this shouldn't work. Because we're gonna run out of memory. So what I'm gonna do is I'm going to refresh this. I'm just gonna do this again. I'm just going to refactor a little bit to not use this list range approach because it's crazy. So what I want to do is, rather than make an obstacles list, what I want to do is I just want to kind of like increment. So we're going to do a list.fold. So we're going to say list.fold. Let me think about this. So a list.fold, we're going to check for stuck in loop. This is going to take in, let's get rid of this obstacle list stuff. I'm going to count this out, and then we'll, so checker stuck in loop. This is going to take in a map. I'm going to call this is stuck in loop. We're just going to keep this around. This is good. Is stuck in loop. Takes in a map and says yes or no. This map results in someone being stuck in a loop. So that's what we had before. What I want to do is I want to get start with 0, 0. Start with my top left coordinate. So initial coordinate is going to be 0, 0. And what I want to do is I want to say list.fold, not list.fold. I want to just loop. So I want to say insert obstacle simulation. And my initial coordinate is going to be 0, 0. This is going to be the obstacle coordinate. So insert point. And what I want this to be is I want this to take in a coordinate. I'm going to use that to create my obstacle list. So it'll be like this. And this is going to be it's a new map. To map, say if is out of bounds, insert point. Then I'm trying to basically loop through until we get to the end. So I think what I really want to be doing is I want to be accumulating how many we found, like what's like the total count. So I'm going to say number of solutions found. Number of solutions found is what I want to pass in. So this is just going to be our recursive function here. So what I'm going to do is say if the point is out of bounds for our map, make the map. I'm going to do something a little lazy here. I'm just going to make the map regardless. To map, where I say get the initial obstacles, but insert my new point there. So that's going to give me a map. I'm going to say is out of bounds. Let me close this. Takes the map first, then the coordinate. Okay. So we kind of want it more like this. But basically, if this is out of bounds, if that new point is out of bounds, we don't want to check it. I don't want to do out of bounds actually. Sorry. What I'm trying to do is I'm trying to make it so that I don't infinitely just keep inserting stuff past the point. So what I want to say is if the position, like the X and the Y, is like, yeah, it's out of bounds. That's fine. I'll just do it this way. Anyway, so if we do that, we're just going to return the number of solutions found. Otherwise, we're going to say found new solution is a Boolean where I say, are we stuck in the loop? So if we find out that we're stuck in this loop, then what we're going to do is we're going to say, all right, we're going to insert obstacles. Simulation. I guess we're going to say find solutions. Find solutions. initially we find 0. So what we want to do is say, if we're stuck in the loop, we're going to add to this number before we call this again. We're going to say, what's the next position? So we're going to kind of like add, we're going to find the next insert point. We got to do that still. But the idea is if we found a solution, found new solution, then we're just going to increment this number. You'll see why I did it the lazy way first, because I just didn't want to deal with all this index math stuff. And that's going to keep looping until we're out of bounds. So it's up to us to format this. Oops. Format that, else if set number of solutions found. Let me do this. So that's the initial coordinate. I don't think we use the initial coordinate because we just hard code it in here. But when I hit compile, it should yell about this. Because what I want to do is basically get the next coordinate. So I'll say, this should be easy enough. Insert point equals if, grab this, coordinate, I'm going to say xy is this. I'll say if the x is greater than or equal to the number of columns, then we're going to return start at 0, y plus 1. Otherwise, we're going to do x plus 1 and stay on the y that we're on. I think that'll do it. 0. All right, hold on. 1 second. 0, simulate the map. Stuck in the loop. Stuck in the loop. Get new map. What changed here? Find solutions. Insert point is 0, 0. If the insert point is out of bounds, we just return the number. Is the insert point out of bounds? 0, 0? I don't think it should be. So what I'm curious about is how many times this runs. I just want to debug.log. Let's debug log this. So this should be running a bunch. So if I compile this, okay, insert point 0, 0, and it says 10, 0. Oh, it's somehow going over the bounds. That's not good. So I'm doing this wrong. The next insert point oops. If x is greater than or equal to number of columns minus 1. There we go. 6. Okay, so I literally forgot a minus 1, and that was the difference there. All right, this should be a lot more memory efficient. We'll see how it goes. But we're creating all these simulations, and we are just doing little variations on the set, and I think that will prevent my computer from getting absolutely cooked. But let's try it on the real puzzle. Input. Maybe it doesn't. I deleted. Wait, did I delete? I just want to make sure I deleted the obstacle list. I'm not still instantiating that list, am I? Oh my. All right, the entire optimization, I just did it anyway. Sorry about that. Save that. I was creating the list and then not using it. I knew something was wrong. I'm like, my code can't be that bad. It can't be that bad, you guys. All right, let's try this out. Oops. Now I'm getting confused. Ooh, no. It can't be that bad. Is this the new one? now I confuse myself. This is good. String. Is there a better way to do this? Let me think of this. So this is already done. So just doing math. It's running my simulation once per grid. You know what I could do? I think I have an idea. We run the simulation once, and we only insert in the visited. Oh, we got the answer. It's too high. We only care about checking the places that that the person had been. So what we can do is we can loop through just the coordinates that were visited, just the 4,800 coordinates. That should still be like the same complexity. It just might be more work. Why is this wrong though? Is what I'm more confused about. Okay, so let me undo this. Compile. It says it's wrong. It says it's too high. Day 6. I don't want to return. Yeah. Okay, I think I have a way to make this go a little faster. I don't know. But the idea is we run the simulation once. Visited without obstacles. Because you run simulate on toMap with the initial obstacles before I run this. Visited without obstacles. And then we say it's the visited. Oops, tuple dot first, then the visited. So this is all the points that the guy visited. So what I want to do is I want to make this a list of like points that I'm interested in checking. So I'm going to say set that to list. Oops. And I'll say list.map. But first, all I care about is this. Okay, so I'm only going to check these, not the whole grid. So the idea is find solutions is not going to increment this. What it's going to do is it's going to take this and it's not going to do bounds checking like it did before. It's going to say, this is my list of coordinates of like points to check. In the case where there are none left, I'm just going to return how many solutions I found. If I have basically an insert point, and then the rest of the insert points, then all this stuff's gonna happen. I don't know. Yeah, we do not the map. We don't need to check this anymore. Sorry about all the indentation confusion. So I don't think I need this either. I don't think I need this. This is going to be the rest of the points to check. I think it's just this. It's giving me 7. Oh, I'm not allowed to do the starting spot. That's what it is. What was the number I put in? 1656? That was all it was. Gosh dang it. Good thing I remembered an arbitrary number. Okay, we did it. That was bad. I think the solution we have here will also work. I am curious to see if it goes faster. Let's see if it let's see if this is any faster. So what we want to do is this, and then we want to remove guard dot position. Oops, set dot remove. Guard dot direction. I did it wrong, but okay, that's the 6. All right, I want to try this. I'm just curious. This is going to be a bonus solution, but we got it. We did it. So it was just my math was off by 1 because I wasn't ignoring that single cell. And so I could just subtract 1 from whatever I got. It's because I didn't follow directions. But anyway, this is doing it without math. Let's see what happens if I put in my big puzzle input. We'll see. But anyway. Oh, that cook. I don't know what's better. Making a list. I feel like allocating a list. The memory footprint. Oh wow, that was a lot faster. It's like we're scanning less space, so we're making less like simulations, which is probably the more expensive part than allocating one list. But yeah, 1655. So that was the answer. That was day 6. So probably a longer video than I expected. But I will be back. I'll put on a hat so it looks like I'm a totally different person, and I'll be back for day 7. See you there. Goodbye.